Hello, everyone. I'm Alex. I work at Google on Chrome, and I'm going to talk a bit about being on the receiving side of a security bug and what we do about it when we get one. Here's how to contact me. This will be at the end as well, so you don't need to write it down. So I work at Chrome. We make a web browser. You've hopefully heard of those. You've hopefully heard of Chrome as well. The web is like an infinitely composable application platform that lets anybody run code on your computer. And that's like a really scary proposition. Like every website basically runs code. The fat bears, the adverts. And it's our goal in Chrome security to make sure that it's safe for you to click on links and load websites. So to make that happen, we put the websites in boxes, and we make sure that their code can't affect any other websites and can't affect your computer. We can't stop you from messing with your computer. That's there for you to have fun with. But we put everything in boxes. The way that we do that is we use operating system processes. So every single website gets given its own process, and we sandbox it down. We completely limit what it can do, and that means that it's very difficult for it to get anywhere else. To the point that if someone gets a bug in a website in V8 or something like that, we believe that we can stop them from getting outside of that arbitrary binary stuff, and they can't get at the rest of the stuff. Some of the other processes that Chrome needs, they can get at stuff, like the browser process needs to be able to get at your computer and your files because it needs to draw things, and it needs to upload files for you and things like that. So not every single process is in the best box. But the ones that are in the boxes, we want them to stay in the box. And now for the rest of the talk, I'm going to be focusing on Windows, but the same architecture happens on Android and iOS as well. Now the next thing we need to know about are Windows handles. So everything that a process can interact with on the operating system is represented by a handle. The kernel keeps track of them, and they represent a thing you can get at and what you can do with it. So an example is if you create a process, you get a process handle back, and then you can use it to kill the process or write to the process's memory. If you want to create a file, you call the create file system call in your process, you get back a file handle that says what you can do with it. Now the renderer, because it's in a sandbox, it can't open files. We've made it so that it's impossible for them to do that. This is really good. This is what we want to be happening. But sometimes we need to be able to send resources into the renderer so that it can read them. And the way that we make that possible is a privileged process like the browser can open the file, and it can do various checks to make sure it's the right one. And then it uses a Windows system call called duplicate handle, which takes the process that you want to take the handle from, the handle you want to send somewhere, and where it's going to go. You call that, and the moment you call it, it zaps, it tells the kernel, and the kernel magics a handle into the other process and gives it a number, and then you tell the other process what number to use to refer to it. So the process can get at the handles that are in its process without you telling about them. It can trawl through the table. But the way that you tell it which one it should be using is through an inter-process communication mechanism, which is a really long word to say, so we actually say IPC instead. So how does this work in Chrome? So again, when we start up a process the first time, we create a pipe for it. Each end of the pipe is a handle. So every process gets created by the browser. There's a pipe with handles you can talk to. That's really great. Now, if process could only talk to the browser, it would be really, really slow to do graphics and stuff on the web. So we need ways for renderers to be able to send images directly to the GPU process, say. The way that this works is we create a little pipe inside the browser with both ends of it, and then we use duplicate handle to send the handles to the other two processes and tell them about it, and they get a nice connection to each other. They can talk to each other. They get a nice little pipe that they can use. Now, sometimes these low-privileged processes, the renderers, need to be able to send an operating system object to one of the other processes. But they're not allowed to do this. They're sandbox. They can't use their connection to do this. It's gets blocked. So part of our IPC protocol, the low-level stuff we have between processes and Chrome, it includes a thing we call relay message, which the renderer can say, OK, I know I want to talk to the GPU. Please send it this handle for me, please. The browser's like, yoink, sends it over there. And now perhaps the renderer and the GPU could share some memory and both understand what they're looking at. Now, you know everything I know about IPC code, at a point in March. Like, I had worked on it years ago, but I forgot all about it. I was sitting there thinking happy thoughts. I was imagining how otters live under the sea and like chill out and eat shellfish and hold each other's hands. And then, oh no! Okay, that didn't happen, but it's cool, right? We get a bug report from Kaspersky, and they're like, here's a DLL that we found, some people using. It's a sandbox escape. Deal with it. And that's our job, right? So we get it, we run it in an A10 build of Chrome, which is like a memory checking special build, and it doesn't crash. And we're sort of like, okay, this is unusual. Normally all the bugs we get are memory safety ones, so this one wasn't one of them. So instead, and normally we wouldn't just run a DLL if you send it to us. Like, we're going to be like, please send us source code so we can read it and compile it ourselves and understand what's going on. But the attackers didn't give Kaspersky the source code. They had to just give us the DLL. We had to like deal with it. So instead, we use like, Sandbox VMs and careful ways to do this. So anyway, we run this in a Sandbox version of Chrome. We use debuggers and sysinternals tools and stuff like that. And at some point, we're like, we realize a handle is popping up in the renderer that isn't meant to be there. And it's a handle to a thread that's in the browser process. And it's got an access mask of 1s and Fs. And like anything that's set in an access mask means you can do something. So like all 1s, it's like really bad. You don't want out. So this is like the problem. Essentially, this renderer can be compromised. It can download this DLL code, run it, and get a handle to the browser process. And then it can use that to like run whatever code it wants in the browser process. So it's a sandbox escape. It's really bad. We don't want this to happen. Kaspersky were right. So now we're going to try to fix it. So a big tool we use for this is time travel debugging, which is a nice new thing that's come out. It's a bit like RR on Linux. We were able to attach to the browser process, record it, trigger the exploit in the render process, and then see what goes on. And then put breakpoints on every duplicate handle, put breakpoints on every receive and send message call in the renderer. There's quite a lot going on. And so it took us a little while to just look at every single one of these, dump some output, find the ones that seem to be interesting. I'm going to use a trace a bit like this, and we're going to do some like time travel as we're doing this. So first we're going to go to the end, because like the first call we see in the bit of code that's sending stuff back to the renderer, we see a duplication of a handle that's already in the browser process of the thread that it's on. And it's saying, please send this message down this pipe to the renderer. And it's sending it to the identity, the process handle of the renderer, the destination there. And this is actually a thing that's fine, because it's how file handles get sent back to the renderer, or how sections get sent there. So it's not the bug, but it's a bit weird. But we're like, where did this come from? If we go a bit later, we see a message getting sent to the renderer with the ID in it, and we see the handle popping up in the renderer. So we know this is the right call to look at. But we need to like time warp, do a jump to the left, and like see what's going on earlier. And so if we look at the receiving, the previous receive call, there's a bunch of other stuff goes on in the render before, but we look at where the receive call comes in. We see a message coming in, and we see a duplicate handle, and the duplicate handle is of a weird FC value. And like, this is weird. It's not a valid process handle value or a thread handle value. It's just a weird number. We're like, okay, this is sort of sus. It's starting to tick things off in our brain about stuff that we know about Windows. And in particular, like a couple of lines earlier before we start doing the duplicate handle, there's a check for invalid values in the code already. So if this had been all Fs, the browser would have crashed and this exploit would be impossible. So this is the invalid handle value in Windows, and so at least we're rejecting that one. That's really good. But we're not rejecting the special version. So why is this a problem? Why does it get through? So like a key to this is in the duplicate handle function. If you read the docs for it, it says the handle you're duplicating must be valid in the context of the source process. I would have assumed that getting to this call with this FC value, it wouldn't work, because this isn't a handle in the process that we're pulling it from the renderer. It's a handle, it's meant to refer to a handle in the browser. But it still happens. We had made a bad assumption about what was going on. So why is this a bad handle to duplicate? Well, Windows has these things called pseudo handles. One of them is the get current process pseudo handle, and that's the all Fs value. And we knew about that, and that's one reason why we were blocking it here. But there's other ones that we had forgotten about. One of them is called get current thread. So we're seeing this duplicate handle call on the receiving side. It says, please take a handle from the renderer that is the current thread, and then eventually send it back to the renderer. And again, we thought this wouldn't work, but it is working. So I went and used Ghidra. This is actual Ghidra output of what was going on inside the kernel when a handle was getting duplicated. And basically, it wasn't looking at the source process handle, where the process that it was coming from. It was just looking at the pseudo handle value that was getting put in, and then short-circuiting and like sending it straight through. So that was like, it makes it a lot faster, but it also makes this bug a lot faster. So you can see why Windows haven't changed it. So putting the bug all together, the renderer sends this message with a fake value in it. We pull it in, we deserialize it, we duplicate it. This magic pseudo handle value gets used. And it means get current thread. So we take a thread out of the browser. Later on, we're like, OK, we should be sending it back. We send it back, and it pops up in the renderer. So that's what the bug is going on. We figured it out. It took us a little while, but we're like pretty confident we can fix it. So like, OK, all we got to do is reject all pseudo handle values. So all the checks we had on deserialization, we turn them into, is this a pseudo handle? And that's basically -1 to -16. Reject them. We never get to this duplicate handle call. We never get to the thing that sends it back. Only valid handles could be sent back. Sweet. We release it. You'll be told to update your Chrome, that little button. Push that when we want you to push the button. It's important. And then what do we do next? So like we fixed the bug. Everyone's happy. What we like to do for these very surprising bugs is do a postmortem. So we ask ourselves a bunch of questions. Could we have known about this already? What can we do to prevent future mistakes? Was it easy to debug? Were there tests? Could we have added tests? What docs are we missing? And like, who else can we rant at? Because like, we've just spent a lot of time on this. Who else can we like tell about it? So could we have known? Yeah, we actually did know. In 2019, we did a big refactor of all of our low-level IPC code. And in that, well, when I came to add the check for is pseudo handle, I went to the file. I was like, oh, it's probably going to go in this file in Chrome. And I start writing, and I realized the function's already there. So we have a check for this already in Chrome. We just weren't using it in the new code. So we rewrote all of this code, and we forgot to put the new check in, or just didn't know about it when we were doing it. So that's a real shame. But we got new code, so woohoo, and a new bug. So then we ask, can we prevent future mistakes? So the way that we do that is we audit for variance. So we spent several weeks going through the code. Every single place that we duplicated a handle, we went back in the stack a bit, worked out where it came from. Everywhere it looked like we were taking a handle out of some untrustworthy data, we made sure that we were like putting the pseudo handle check in there and just not letting this happen anywhere else. So hopefully it'll be impossible to do this again. Another way to prevent future mistakes is you make things unrepresentable or uncreatable. So in Chrome, we wrap handles in like a C++ type. And it used to be possible to make them out of pseudo handles. So you could put the get current process value in, and it would give you the current process handle in this wrapper. So now that doesn't work anymore, it explodes. And it's very rare cases people need this, so we make them go through little dances to make it happen. And the other thing we can do is we can prevent important handles getting sent to untrusted processes. So we used to just do that. We hope we would get it right. But now in the transfer handle function, it turns out we already had a decheck there that it would run in our developer debug builds. And so if a developer wrote code that deliberately sent a thread handle to a renderer, it would crash for the developer. So we basically enhanced that a bit and turned it on in production. So now it should be impossible for the browser to send anything except a very small list of handle types to the renderer. So it should be a lot safer. Next was this easy to debug. And can we write tests for it? And it really wasn't, because it's in a really complicated part of the code that nobody really understood because we'd forgotten about it because we did it 3 years ago. And it's really difficult to test because the best way to fix it was to crash. And it's really hard to write death tests in Chrome. So after the initial fix, we went and did a better fix, one where we used things like null opt to return an invalid thing as opposed to like crashing. And then you can actually test the thing that makes the null op. And then you know that the crash is going to work. So now we've got tests. We're not going to regress this, and we're not going to do it again. Are we missing docs? Sure, we were missing a lot of docs. Like I went searching for stuff about handles. We didn't have anything in Chrome. And the Microsoft docs about this are pretty bad. So we're like, OK, let's improve the situation. So we've written ourselves a little one-pager. It's in the Chromium source tree. So anyone searching for handles is going to find this. It's linked from all the important places. And it's basically it's like crypto. Don't roll your own handling code. Like use the stuff that we've already provided. And then who else can we rant at? So I raised a case with Microsoft about this because this bug also affected Edge. The duplicate handle behavior is really awful. And they were like, it's not going to change, but we're going to improve the docs. And this is how they improved the docs, and I'm a bit confused about how it's improved it. But they did change the docs, so that was something. So phew. We've gone through a process of fixing the bug, And then we've put lots of other barriers in. We've hopefully improved in lots of other places so it can't happen again. Like we've used the momentum of a problem to like get more work done and hopefully make this much more difficult in the future. So, you know, I'm pretty happy. I'm chilling out. I'm thinking about odders again. Like it's my favorite. I'm just like, oh, this is so great. A few weeks later, oh no! We get a bug report, another bug report. This one is a bit more complicated, and this actually involves source code, which is really good. It involves a patch to the Chromium renderer. Someone's like, I can set up a few connections, and then I can send this packet, and I get a handle again. And I'm like, oh no. Anyway, so you need to know a little bit more about IPC mechanism, about how this works. So the pipes between the processes, they are represented in like at a low level in Chrome as a transport. And that has the handle, but it also has a bunch of metadata about what's on the other end of the transport. And so when we create a thing in the browser, it knows it's talking to an untrusted process. And the untrusted processes know they're talking to the broker. And so that we use that to work out what we can send where and like what to trust. There is a weird situation in Chrome where sometimes we need to create like a separate universe of IPC stuff going on. So part like the updater does this and the notifications things do this. And so we sometimes need to create connections to things that we like trust and allow them to do like powerful things for and send them things. So this is like, it's necessary. And for these things, we have to be able to send them process handles and thread handles. So the check that we added before doesn't operate on these. You can perhaps see where this is going. So this bug sort of works by, you know, you've got the browser and the renderer. The renderer can send a request introduction message, and it lies about who it is. It says, I want to talk to something over here. The browser sends back, here's the transport to the thing you just mentioned. The renderer gets it. It then sends it back to the browser in a completely unrelated message and says, you wanted to talk to this guy, right? He's over here, and he's a broker. And he's got your process ID as well. And so this pops back up in the browser, and the browser thinks this is a connection from itself. It's a messed up situation that shouldn't be happening. And so this allows the renderer to send this sort of similar message to the one that got sent in the previous bug to the browser. And to the browser, it looks like it comes out of itself as well. So it gets to the same code path we were in before. So the broker sees this coming out, the browser sees it coming out. So it thinks any duplication is going to come from its process handle ID. And the handle gets provided in the buggy packet. The all F's value doesn't work anymore. The all F E doesn't work anymore because it still hits that check. But this is a valid value for a handle to have. And if the renderer guesses right, it can find one in the browser process because Windows uses like it starts with 4 and then goes 8, and so you get an ordered list in the browser. Which means you can guess, because like in startup, the main thread gets started at a certain time. It usually gets the same handle. You can sort of guess a handle. So this duplicate handle call, it works again. And because we've confused the browser into thinking where this is coming from, it works. It's a perfectly valid call to be doing. It's an actual handle, so it doesn't hit the checks we put into the representation things before. It gets back to the sending it back. And then because we've lied to it about what's at the other end, it's like, I don't need to do the check for sending handles to renderers. I can send the handle to the renderer. So the renderer gets it. So it's an all-access party pass in the renderer again to the browser. It's pretty bad. This one is not as reliable as the previous one because the duplicate handle call closes the source handle when it does it. So you might zap the thread that's actually running, or you might zap some other important handle if you guess the wrong one. So it's not as good for an attacker, but I think it's useful, and some people might use it if they found out about it. Anyway, so it happens. It's bad. The fix is pretty obvious. Don't trust the untrusted process. So we just make sure that the trust information gets passed down, all the things that do deserialization, and we just don't accept it. And we kill the renderer if it sends us this bad stuff. We're like, you're bad. We're not talking to you anymore. Go away. And obviously, this was a surprise. So we do another postmortem. We're like, okay, let's also see what else we can try and fix. So could we have known? In this case, I don't think we could. We had spent 4 to 8 weeks looking at this code really, really hard. I think we'd understood and got as far as we were going to get ourselves. But we have a VRP. We pay people a lot of money for telling us about bugs like this. We paid this person over $200,000 for telling us about this thing they saw because they saw a patch and then did a bit of work and then told us about another thing that might happen, a variant. They hadn't even seen the public text of the first bug when they sent it to us. So get a VRP, treat your VRP researchers really well. Like I helped this person write the exploit. That helped us pay me with more money. So it's cool. Was this easy to debug? Was this easy to debug? It was not easy to debug. Like this message generation code, it's like the most amazing 1980s macro mess. It's brilliant. So it's elegant, it's beautiful, but it's horrible. So like when you're debugging, like you hit this for every single message. You can't put breakpoints in because you can't put a breakpoint in only one of the functions. It would break in every 70 message passing would happen. We didn't have any message dissectors for this sort of stuff, and the structs are generated by these macros. So I had to like figure this out by having a markdown file and like commenting every single byte in the message to work out what's going on. It's not a fun time. So let's not do that anymore. So we've moved to a situation where we have the messages shapes in like a data file, and we can use that to like make some Python structs and do packet dumps. And we can also use it to generate and check in the full message processing code. So that's like made it a lot easier. And now you can open that file anywhere. You can put breakpoints in exact places. You can put printfs in. It's so much nicer. Like this seems like it's going to save you time. This helps you fix bugs. The other thing that we realized we weren't doing very well is we were not validating stuff off the wire very well. In particular, the trust. But another thing another class of bug that comes up when you're dealing with in C++ is that the compiler is allowed to assume that any enum class value only ever has the values that you've written in the source code. So in this case, like 0 and 1. And it can assume that any bool is only 0 or 1 on the final byte of the bool. And it can generate code that like might be a jump table. So when it switches on an enum value, it can jump. It can be basically like go to here 1 or 2 or 3. And if 3 doesn't exist, it's just going to like jump into the middle of nowhere, which in certain circumstances can mean arbitrary code execution. And so we weren't validating that all of the bools and the enums were in range on the network for these IPCZ packets. We do it for the normal IP packets in Chrome, the Mojo ones, but we don't do it for these ones. So we put that in, and it was a lot easier to do that because we were in the code generator. We could just generate the checks into the code. It was so much simpler than trying to fix the macros. And so, yeah, we have stuff like this in here now, which is sort of fun. So I'm happy again. There will be no more bugs in Chrome. Although, if you want to spend 3 months staring at IPCZ packets, you might find one. So I think it's a good target to go look at if you're so inclined. So, like, what can we get out of that? So you can be more security by doing the same things that we do here. So first, you've got to fix the bug. Like, definitely do that. Release it to people. But then you've got to postmortem, and you've got to follow up. Like, really think about what led to the bug happening. Be blameless about it. Like, I was involved in the code reviews for all this stuff. I wrote some of this code. Like, you're going to make mistakes. Be happy about it. But then try not to make more mistakes in the future. Have a VRP. Treat the VRP researchers really well. Like, help them understand their bugs. And then pay them really good money when they come to you with really good bugs. Definitely do that. Reduce complexity and cleverness. Like, I think the IPCC code is complicated, but I think it has a level of complexity it needs to solve the problem it's solving. But some of the complexity, like the macro stuff, wasn't super necessary. Try to make wrong things impossible. Like, if you crash the moment something weird is happening, a lot less weird stuff happens. Improve your debugging tools, fix the docs, complain at Microsoft, but never expect anything to happen. And if you don't remember anything else, do a postmortem and follow up. Like when you get a bug report like this, your org starts caring about you, and you can get a lot of momentum of understanding of the code you're looking at. Like, I didn't understand this code at all, and then I fixed the bug, and I suddenly understood it, and I could make all of these extra improvements. So use that momentum you get and that permission you get to do some work to follow up to try to make things harder for people in the future. Yeah, so here's some deets and props. Thank you to the unknown threat actor. Kaspersky they've written a blog about this. They think it was the follow-on of Hacking Team, but I can't speak to that. Google Tag helped us a lot. Chrome Security is great. Here are the CVEs and everything. And this little guy here is Bug. He's our little Chrome VRP mascot. So thank you, everybody. And